So welcome to session 5 control systems, subject code 18EC43. So in the previous class we were saying about this one, that is the derive of means develop a state transition matrix from the state equations. Okay, so it's a continuation part of that. So here we are considering some more examples here. So let us consider in the previous thing we have considered with the problem by giving when in the given data they have given only A matrix, and also in the problem where they have given A, B and x of 0, A, B and x of 0. Okay, and here the problem what we have considered is, so here they have given A and they have given B. Okay, not the x of 0. Okay, so here x of 0 is not there, only they have given A and B. Okay, so if this is a case, this is a second derivative two state variables are there and A matrix is there, B matrix is there. Okay, for this one how to develop the STM, that is state transition matrix. So we know that is pi of t is equal to, that is L inverse into Si minus A inverse. Okay, but here as we know, that is ZIR, that is 0 input response and ZSR. Okay, so here x of 0 is not there, means ZIR is not there. Okay, so here that is pi of t is only if you calculate S minus A and take the inverse of that, and if you take Laplace inverse of that, then you will get the pi of t. Okay, so already we know that is 2 is to, again it is 2 is to 2 matrix, and here Si minus A, and here this is Si minus, this is Si. Okay, A is 0 1 minus 2 minus 3, and if you do the matrix subtraction, that's S minus 0 S, 0 minus 1 minus 1, and 0 minus 2 minus of minus 2 will be 2, and S minus of minus 3 is plus 3. Okay, so this is Si minus A. So adjacent of that is nothing but, as we know, that is cofactors of transpose. Okay, the cofactors is nothing but these two will exchange, S and S plus 3, these two will exchange, and here and minus, so 1 will come here, 2 will go. Okay, so 1 2 will go here. Okay, and after this again the transpose of that, so directly we are writing adjacent of Si minus A. So after transposing, okay, so after the transpose it will become, because S plus 3 will be here, so this is nothing but S plus 3 and S here, and it will be 2 and it will be 1. Okay, it will be 1 here. Okay, before the transpose. Okay, so after the transpose this will minus, so after the transpose this will become Si. Okay, S plus 3 and 1 will come here and the 2 will come here. 1 second. Okay, so initially it is like this. So transpose of the cofactor of this will be S plus 3 and S, and here it will be 2 and here it will be 1. Okay, so after that if you go for the transpose of this, okay, and then it will be again, so S plus 3, the plus 1. Okay, and here the sign will change here. Okay, so S plus 3 plus 1 and minus 2 and S. Okay, this is directly adjacent of Si minus A. So now we know that Si minus A inverse is adjacent of Si minus A divided by determinant of Si minus A. Okay, and here, okay, determinant of this is S into S plus 3 minus 2 into minus 1, this will become S square plus 3S plus 2. Okay, and here this inverse is adjacent, already we have Si minus A we have taken, that this is adjacent and this is determinant. If you apply both, so then inverse of Si minus A inverse we can give as like this. Again we need to split in terms of s plus 1 separate and s plus 2, and similarly here s plus 1 s plus 2. Okay, so which will be given that si minus a inverse is nothing but in this term. Now we need to take the Laplace inverse. Okay, if we take the Laplace inverse of this one, then we will get a term 2 into e raised to minus t minus e raised to minus 2t. Okay, and similarly that is 1 by s plus 1 is equal to e raised to minus t, and minus of 1 by s plus 2 is e raised to minus 2t. Okay, so this together we call as pi of t, that is the state transition matrix. Okay, so here what we did is, here only they have given a and b here. Okay, and here they have taken adjacent of si minus a, si minus a inverse, then we need to take the inverse of that one, Laplace inverse of that. Okay, so the next one, here the problem they have given a term and b term and also again x of 0, so like the previous one. Okay, so if the problem is, if they have given x of 0, then we need to take the, obviously we need to calculate ZIR and ZSR. Okay, so we know ZIR is equal to Laplace inverse of, we know ZIR is equal to Laplace inverse of x of s into x of 0. Okay, so pi of s is nothing but si minus a inverse, that is nothing but adjacent s minus a divided by determinant. Again it is 2 is to 2 matrix. This is si and this is a, si minus a is this one, and adjacent of si minus a, okay, we can give as it is change here. Okay, AD, okay, this will be changed and this will again change with respect to signs here. Okay, and the determinant we can give as s into s plus 2, and anyway this is 0. S into s plus 2 is nothing but s square plus 2s. Okay, that is s into s plus 2. So that is pi of s is equal to, so 1 by s into s plus 2, and this is adjacent of si minus a. Okay, and this will be given by, that is s plus 2 will cancel 1 by s. Okay, and that is 1 by s plus 2, and this term, third term is 0, and here 1 by s plus 2. Okay, so that is we call as the pi of s. Then after getting the pi of s, we need to multiply with x of 0. X of 0 is 1 0. Okay, so 1 0, and the only the remaining term will be, okay, the remaining term will be 1 by s 0, because this term will be 0, that is 1 into 1 by s, and this term will be 0, 1 into 0 0, and this term will be 0. So only 1 by s will be remaining. So Laplace inverse of 1 by s, it will be 1. So ZIR will be 1 0, it will remain with only 1 0. So once we calculate ZIR, we need to go for ZSR. So already we calculated the pi of s, that will be multiplied with 0 1. Okay, and here it is 0 1, so only this term will be remaining, that is 1 by s plus 2 and 1 by s into s plus 2 and 1 by s plus 2. Okay, so that will be multiplied with u of s. U of s is 1 by s, again it will be 1 by s square s plus 2, 1 by s into s plus 2. Okay, so whatever this term, so we can represent individually like s plus 2 term and s square term. So that will be given as 1 by s plus 2 1 by 4 divided by s plus 2 minus 1 by 4 s and plus 1 by 2 s square, divided by, similarly s into s plus 2 we can represent 1 by 2 s minus 1 by 2 s plus 2. Okay, so if you take the inverse of this term, Laplace inverse of that, then we will get 1 by 4 into e raised to minus 2t, that is 1 by s plus 2. Okay, again this 1 by s is constant, so 1 by 4 remain as it is, and this is 1 by 2 t. Okay, similarly 1 by 2 minus 1 by 2 into e raised to minus 2t. Okay, so this is nothing but ZSR. So once we get ZSR and ZIR, we need to add that one. So ZIR plus ZSR. So 1 0 plus, we get ZIR is 1 0 plus this term. So this will become, that is 1 by 4 e raised to minus 2t plus t by 2 minus, that is 1 by 4. Okay, so this is overall we call as x of t. Okay, x of t for the two states variables. So this we call as state transition matrix. Okay, so in both session, the 4 and 5, so what we have calculated is, if the given matrix is only A, okay, or if the given matrix is only A and B, and if the given matrix is A, B and x of 0. Okay, if that is, if x of 0 is given, then we need to find out ZIR plus ZSR. Both we need to calculate individually and we need to add. If it is only A or AB, then directly only S, the Laplace inverse of okay, the Laplace inverse of S minus A inverse. So that is enough to calculate the state transition matrix. Okay, if there is no x of 0. Okay, so these two sessions will we have seen how to develop the STM for the given state equations. Okay, so the two problems, totally the 4 problems, so we have considered here.